Bé, anem a començar. Bona tarda a tothom, benvinguts, benvingudes. Ja sabeu que a finals de desembre la tradició és fer l'assemblea anual de socis, però aquest any ja en vam fer una a finals de curs per poder també repartir els temes i tenir més possibilitats de dialogar amb la comunitat matemàtica, amb els socis i les sòcies, però mantenim també aquesta d'avui per la segona part i amb la tradicional conferència important que la precedeix. Per tant, és un plaer tenir avui la Marta Mazzocco, que s'ha incorporat a la comunitat matemàtica catalana i que, per tant, també ens semblava molt bé aprofitar aquesta ocasió de tota la societat per convidar-la i que així fos també una mena de benvinguda i una invitació. És una persona que a nivell associatiu és molt activa, ha col·laborat molt amb la London Mathematical Society. Deixeu-me compartir una anècdota que aquest estiu, quan estàvem al Congrés de la Societat Matemàtica Europea, hi va haver una trobada d'aquelles que fan així més institucionals, en petit comitè, que organitzava la London Mathematical Society. I parlant de la catalana i tal, de seguida el president va dir però és que ens heu pres una persona molt important i molt significativa. So the president of the London Mathematical Society was saying to me that he was you. So we are happy to win. Evidentment les relacions han de ser bones i volem que millorin amb la London Mathematical Society, però estem molt contents de tenir-la aquí. Seguidament, sense més dilació, donaré la paraula a Eva Miranda, que molt amablement ha acceptat de fer-ne la presentació. Gràcies.
Moltes gràcies. Bé, és un plaer immens per mi estar presentant la Marta Mazzocco, que farà la xerrada que no sé com dir-li. Jo proposo que li posem un nom, com, no sé, col·loqui de Nadal de la Societat Catalana de Matemàtiques. Venim vestits de Nadal.
La conferència d'hivern?
O conferència d'hivern, exactament, per no ferir sensibilitats. Doncs per mi és un plaer introduir la professora Mazzocco. La professora Mazzocco no només és una figura destacada en el camp de sistemes integrables, sinó, diríem, una force of nature o una força dinàmica en la connexió en anàlisi, geometria, física, matemàtica i àlgebra. Entre les seves moltes distincions n'he triat una, perquè ha de ser curt, no? I doncs ha estat European Mathematical Society Distinguished Speaker aquest estiu, que és un reconeixement que subratlla les seves excepcionals contribucions a les matemàtiques. De fet, els seus assoliments, com ja has destacat tu, van molt més enllà de la seva pròpia recerca, sempre demostrant la capacitat de lideratge i visió. Ha tingut un paper decisiu en el mentoratge de nombrosos matemàtics joves i ha contribuït de manera immensa a la comunitat matemàtica. A més, ha format part de juntes de direcció de prestigi, com l'Estació de Recerca de Banff, el Centre Internacional de Centres Matemàtiques, la London Mathematical Society, on el seu paper de defensa i representació de les dones en matemàtiques ha estat molt important. El seu viatge acadèmic comença amb un doctorat en física matemàtica a Suïssa, a Itàlia, l'any 1998, seguit d'estades d'un contracte postdoctoral a MSRI a Berkeley, i després va continuar la seva carrera en institucions molt prestigioses del Regne Unit, Oxford, Cambridge, després Manchester, Loughborough, i un punt important a la seva carrera va ser el pas de Loughborough a la Universitat de Birmingham l'any 2018, on va crear el grup de recerca de geometria i física matemàtica. I això em recorda que Marta is a creator of big miracles, and we are truly fortunate and deeply honored to have her among us since September as ICREA professor, where she's already pulling all her superpowers, to improve our life and mathematics. Her contributions to the field of isodromic deformation, Frobenian manifolds, quantum Teichmuller theory, and mirror symmetry are at the forefront of contemporary mathematics. And today's talk is Segre surfaces and Painleve equations, promises to be a journey through the nice interplay between algebraic geometry and integrable systems through the lens of these Segre surfaces that you will explain. Professor Mazzocco will offer us an insightful perspective into these structures and their remarkable properties. We are truly privileged to have you here. Please join me in welcoming Professor Marta Mazzocco.
Oh, you are leaving me?
Yes.
Oh.
You're in your talk and we're going to listen.
Well, I wanted to thank you very much for the introduction, and I feel very honored. And I'm super happy to be here. So it sounds like you should be grateful, but I am the grateful one. I'm so happy to be here. I'm happy to be in Barcelona. I'm happy to be at UPC. I'm happy to be in Catalonia. I'm happy to be in this room here right now. And I'm also happy to go later for dinner. So I'm very happy. Okay, so I thought of giving you a talk about some recent work, but I knew that perhaps some of the audience would not be experts in my field, so I thought of telling you a few stories, and hopefully you will enjoy. So first story is about the Painleve equations, and so I just wanted to tell you a little bit about Paul Painleve, because Paul Painleve was an interesting human being. He was a mathematician, but he was also a politician, and he was Ministry of War in France, and in 1908 he was among the people who witnessed Wilbur Wright flight in Le Mans, and actually Paul Painleve was a passenger on that flight, so that's quite amazing. Quite a brave person, I would say. I don't know if in 1908 I would have climbed on a plane with Wilbur Wright, to be honest. So excuse me? Oh, no. He then became prime minister, and this slice here, well, the French people didn't seem to be very happy about this because it was the Ministry of War, so they depict him with a bloody sword. Anyway, so he then became prime minister again. So it was only 9 weeks in 1907, and then he became prime minister again at the end of the 1930s. And he was among the people who was behind the famous Maginot Line. I don't know if you know about the Maginot Line. Was a fortification between France to avoid invasion from Germany. Oops, they forgot Belgium. So that was a little problem. But anyway, so even great people can have some, how to say, distractions. Anyway, so why I talk about this guy is that he started a program of classification of second-order differential equations. And the reason he realized that when you solve differential equations, you might encounter some functions, which are the solutions, which are quite interesting and important. So he set to start and classify differential equations of a special form. So he assumed that the second derivative appears only linearly. T, even though it's T in my notes, it's supposed to be a complex number, okay? And then on the right-hand side, you have some function, which is a function of the dependent variable, usually rational, in the dependent variable, polynomial in the first derivative, and then rational again in T. And he was requesting two properties for these equations. The first property is so-called Painlevé-Kowalewski property. I will explain in a second what that is. And the second property was that he was looking for equations whose solutions would be non-classical, therefore new functions, something they didn't know at the time. Okay, so I would like to tell you a little bit about the Painlevé-Kowalewski property. I think people normally call it Painlevé property, but in fact, the inventor of this property is Sophie Kowalewski. So Sophie Kowalewski was working on the problem of the dynamics of the rigid body motion, and she was interested in understanding when we can solve the equations of the rigid body. And may I say that so far, the way people would study solvability was to sit down and try to solve it. Okay, so she approached the problem of solvability in the sense of there must be some property about the system that allows me to eventually solve it. And this is a translation into English. Sorry, I didn't find the Catalan version of her letter, very famous letter to Weierstrass, in which she describes, this stopped working? Oh no. She describes her result, and she starts the letter saying, okay, I'm considering the differential equations of the rigid bodies, I'm not going to go through the notation anyway. And then she says, I found there is a new integrable case. At the time, there were two integrable cases known, one by Euler and the other one by Lagrange. Euler is free rigid body, and Lagrange is the spinning top. So you have a symmetry, and then you have the pull of gravity. But how did she find this case? She set a property. So she assumed that the solutions must be single-valued analytic functions of time. So first of all, I think that's amazing, because essentially she's telling you, okay, I don't care that actually time is real and actually on the positive real line. She's saying, if I want integrability, I must have that the solutions must be single-valued in complex variable, okay? And not only, but she says, single-valued analytic functions of time which have no singularities but poles. So she doesn't like branching, she doesn't like logarithms, she doesn't like essential singularity. So this is precisely the Painlevé property. So you impose that your equation must have solutions which, away from where the equation itself is singular, only can have poles, okay, isolated poles. What this means practically is that whenever you take a T0 around which your equation is analytic, then you should be able to solve locally by power series. Maybe this power series will have negative part, which is the Laurent part with the pole, but Laurent series, which is beautiful. It's something we can handle, we can calculate, okay? So that's the Painlevé property, but it's Kowalewski. Anyway, the second property that Paul Painlevé decided to impose was that he wanted the solutions to be new functions or non-classical functions. I mean, there is a very easy definition, which I've put here in this slide, which is you take Abramovich and Stegun, and then you realize that Painlevé solutions are not there, so this means they are new, okay? But of course, this is time-dependent definition. By the way, I put a picture of Stegun because I just discovered recently that she was a woman, and I think it's nice. Irene Stegun. Okay, that's Irene Stegun, the one. Yeah. Okay, so anyway, so when I say it's time-dependent, is that the new edition of Abramovich and Stegun is actually the NIST digital library on special functions, and the monkeys have put Painlevé transcendence at number 1032. So this definition that I used to do for my slides is not good enough. I need to give you a better definition. And it's quite interesting. I'm going to give it to you because it's not difficult. So the idea is that you start with rational functions, okay? Rational functions, we love them. They are very easy to write. And you put them in a ring of rational functions, and you make this ring with the differentiation. Okay, we can differentiate rational functions. And by the way, when we do that, we again get a rational function. Okay, so I start with the K0. I call K0 my differential field. Oops, sorry. I'm not mastering this, actually. But anyway, so I start with K0 rational functions, and then I allow a set of operations. For example, integration, which if we do it, for example, to 1 over z, allows us to introduce logarithms. We allow derivation. We allow solutions of linear ordinary differential equations with the coefficients in K0. This, for example, puts in all the functions in Abramovich and Stegun. From this operation, we put all these functions together, and we create a new differential field that we call K1. And now we proceed by iteration. So at step n, we will have some differential field Kn. We allow all these operations and add the results of all these operations to the field to create Kn plus 1. I would like to say that this is disgusting, okay? So can you imagine solving a linear differential equation in which the coefficients are hypergeometric functions? I mean, it's highly complicated. Nonetheless, what is the definition of a non-classical function? It's a function that does not belong to any Kn. And the theorem about the Painlevé equations is that the generic solutions are never in any Kn, which, if you think about it, it's kind of amazing. Anyway, this, when I'm talking about Painlevé and his work, we are talking about beginning of 1900, and this theorem was proved by Malgrange and Umemura in the late 80s, okay? So a few years in between. And there is general, a little bit of war between the Japanese and the Chinese, but the French, sorry, Japanese and French, but okay. French didn't do the Maginot Line with Japan, so anyway. Okay, so I'm giving you the list. It's not really that I'm going to use it. I just feel that it's important to list the famous 6 Painlevé equations. As we see, each of them has, some of them have parameters. So, in fact, each equation is a family of equations. And so if we start at the top with Painlevé 1, the right-hand side is a polynomial in W, and it's just t, right? So the only singularity this equation has is at infinity. So what it means is that the solutions, thanks to the Kowalewski-Painlevé property, the solutions of this are always going to be meromorphic functions on C, okay? As you go down, the equations start to catch some further poles, for example, when t is 0, or even for Painlevé 6, when t is 1. So the statement of the Painlevé property is that away from these points, we can always solve by power series. However, there is the second statement that says that the solutions are some new transcendental functions, but this statement we should be careful about. It's a generic statement. So generically, the solutions are new, but that doesn't mean that there are no solutions to the Painlevé equations which are special, for example, rational, algebraic, or even linearizable to a hypergeometric equation. So a lot of mathematicians from the beginning of 1900 to now are working, have worked on trying to find special solutions to these equations, whether special can mean whether they are rational, linearizable, or simply whether the asymptotic behaviors near the critical points of these solutions are special in any way. So what I want to propose here is a modern approach to this problem, which is studying the moduli space of solutions. Moduli spaces are spaces in which the points are classified up to some equivalence relation, and different points may have very, very different properties, okay? It's like the antithesis of a topological space. So points are different in a modular space, okay? And so I'm going to list the moduli spaces associated to each Painlevé equation, if it turns the slide. Okay, so in the case of the Painlevé equations, the moduli spaces are algebraic varieties, okay? So they are zero sets of certain polynomials. I have made here a list, and for each Painlevé equation, we have a polynomial. The zero set of that polynomial is the moduli space of the solution. What does it mean? That I pick a point in this algebraic variety, that point will correspond to certain solution. And you may say, why are you doing this? Well, the point is that the beauty of this is that the algebraic geometry of the moduli space and the geometric properties of these algebraic varieties are telling you things about the solutions, okay? So if you have any of these algebraic varieties and can find, I don't know, for example, a line, a straight line in them, then what you find is that the solutions which correspond to the point in that line have different properties with respect to the other points, okay? And this is precisely what happens. So I presented this list, I should say this list of moduli spaces is based on the work of a zillion mathematicians. I've written only 4 people, Jim Boitz, Clarkson, and Kitaev, because maybe they have the most papers on this subject. But there are really, if I were to quote everybody who's come up with this stuff and contributed to this, it would be just one slide of names, so I don't want to do that. I also quote Saito and Van der Put because they were the ones to put them together in a table, which was clean, and so I think, well, you may say, well, what's that? But actually, it was quite a lot of work to clean up all the work of these other people. So anyway, so let me give you an example. So I'm going to take the example of Painlevé 1, and I'm saying, okay, let's consider this is the moduli space of Painlevé 1. What does it mean? I pick any point here, and it will give me a solution to Painlevé 1, okay? Now, this algebraic variety happens to have 5 lines. In fact, I think you can see them. So in this plot, which, okay, I don't know, can you see the magenta one? Yes. The blue, the red, green, and light blue. Okay, phew. Anyway, if you didn't see them, I wrote the equations there. And the work by Joshi, Kitaev, and Van Spandunk and Vonk shows that corresponding to those lines, the solutions have very special behavior. In particular, they are the so-called Boutroux-Tritronquet solutions, which are solutions which are pole-free in a very large set of the plane. So they are special in that sense. They have a very special asymptotic behavior. So this is just an example. I will now, this is at the bottom of my list, right? Painlevé 1 is the bottom of the list. Now I'm going to go at the top of the list, and I will tell you about Painlevé 6. So Painlevé 6 has a much more difficult, okay, algebraic variety. It has parameters in it. They are called omega. I should remind you, Painlevé 6, the equation had also parameters, 4 of them, so there is a one-to-one correspondence, but I don't want to write it down. So we have, again, an algebraic variety, and this surface, it's very beautiful by itself. It has many, many applications in mathematics. I gave actually a talk at the Faculty of Mathematics a year and a half ago about this. So I just listed some of the properties which are not going to be discussed today, but let me just say that this algebraic variety is also the character variety of a sphere with 4 holes. It arises in singularity theory. It is self-mirroring, mirror symmetry. It's related to number theory and Markov numbers. It's related to cluster algebra, so it's immensely rich. But anyway, what I wanted to say is that in algebraic geometry, this surface is a del Pezzo surface of degree 3, and it has 27 lines. So whilst in the Painlevé 1 case we had only 5, here we have 27. And again, there is a beautiful work by Guzzetti and then picked up by Klims, I don't know how to read, I mean, he's from Czechia, so Klimes, I don't know. Anyway, so each line corresponds to very specific asymptotic behavior again. So these two examples are just to show you that geometric properties of the moduli space and the points in the moduli space tell you something about the solutions of some equations that you don't know how to solve by definition. So it's quite of a nice, I think, perspective. Anyway, so, right. There is another thing I wanted to say, en passant, is that for all of the Painlevé differential equations, the 6 famous Painlevé differential equations, which have then been fragmented in actually 10, but that doesn't matter, the moduli space has a universal form. So I showed you very quickly before a table, so let me just go back, oopsie. And there are some common features in this table. All of these algebraic varieties can be written in the form that I have here above, in which you specialize the red parameters, epsilon, which can be either 0 or 1, and the blue parameters, okay? So there is a universal description, and the beauty of this universal description is also that you can obtain from one algebraic variety the next one in the list by a procedure which is called confluence. So the geometric properties in the confluence are preserved. So if you have 27 lines and you confluence, these lines merge, but they don't break. So if I say something about Painlevé 6, I can confluence it down through all the other Painlevé equations. And the other way around, if I'm able to say something about Painlevé 1, I can try to pull back that information up the list, okay? So it seems like we have a wonderful way to deal with these equations, and I could go home, but the Maginot line, he forgot. There are not only differential equations in life, there are also difference equations, Q-difference equations, elliptic equations. So there is now a new classification which is due to Sakai, a very clever student of Jimbo, former student, I should say, professor himself now. And he actually classified 22 Painlevé type equations, and these include difference and differential. So, okay, there is a diagram. I'm not going to explain everything about this diagram, but maybe I can, okay. Let me tell you at least something about this diagram. So every entry in this diagram is an equation, okay? The red ones, can you see the colors? Red, orange, blue, and green, possibly? Okay. So the red ones are the differential equations, okay? So Painlevé 6, 5, 3, and its emanations 1, 2, and 4, okay. The labels are some symmetry groups. Maybe the way I can explain this is that I told you the algebraic variety associated to Painlevé 6 had a singularity of type D4 inside. Oops, well, okay. So then actually you can prove that the algebraic variety of Painlevé 5 is the versal deformation of an A3 singularity, and so on and so forth. So these labels have a meaning, but it's not important for us. What I want to say is that there are some orange Painlevé equations. These are difference equations. There are some blue Painlevé equations. These are Q-difference. And there is one elliptic Painlevé equation, okay? This is the whole list now, or at least we believe, unless maybe there is another Belgium hiding somewhere else. Anyway, the question now is whether we can study the solution spaces or the moduli spaces of such equations also, and whether we can collect all these moduli spaces into one universal object. And so the work I'm presenting today is about some answer, and the answer is maybe. Okay, so it's not very complete. So what we do is we have focused on this guy, and so for this guy we can also study the moduli space, which will be given to you in a second. And we also hope that for all of the people who are on the right-hand side of it, and we can reach some universality. We haven't yet realized what to do here, okay? So it's a partial answer, okay? Partial but nice, okay? Right, so I will start from this element here, and what I'm going to show you is what it is, its moduli space, and then I will try to understand how to go from this moduli space to the moduli space of Painleve 6, because there is an arrow which says I can confluence, okay? So I would expect that I can map one moduli space to the next. So the moduli space of solutions of the QP6, which was that guy, is given by an algebraic variety, which is a 6-parameter family of Segre surfaces. So I would like to say a couple of words about Segre surfaces. So it's interesting because so Segre surfaces were actually introduced by Benjamino Segre, who was professor of mathematics at the Politecnico of Torino. But then they were studied by his son, Benjamino Segre. Benjamino Segre was professor of mathematics at Bologna University. And why I like this story is because Benjamino and I, the father is Corrado, the son is Benjamino. Benjamino and I have the birthday on the same day. And there is also another common point is that during the Nazi period, not that I lived in the Nazi period, but anyway, during the Nazi period, they had to flee the country, and Benjamino Segre went to Manchester University, where also I got my first permanent job in the UK. So I think that, yeah, okay, anyway. So, and I just...
He didn't get ICREA here.
He didn't get ICREA because, well, no, I don't think it existed. It didn't exist. I think it would have been, but yeah. Anyway, so that's a story. Anyway, so what is a Segre surface? It's normally it's written slightly differently from what I'm writing here, because normally you write this surface in the projective 4-dimensional space, and a Segre surface is given by the zero locus of 2 quadratic equations. Here, I'm writing it in 6 variables, but you see, two equations are linear, so you could imagine to solve, for example, by Z1 and Z4, and place them into the other 2 equations, so you can see that it's 2 quadratic equations in CP4, okay? So it's just that it came up to be more useful to write them this way. So it's a 6-parameter family. The parameters are oddly called rho 2, rho 3, rho 5, rho 6, and lambda 1 and lambda 2. I think at a certain point we had so many parameters in that paper that this decision sort of was that we wanted to carry the index in the parameter should be the same as the index of the variable in which it was appearing in front, because otherwise we were going crazy, okay? Anyway, so there is this 6-parameter family. And now I would like to give you some properties about this. Okay, so I said this appears as moduli space of the space of solutions of QP Painleve 6. And what we prove is that if you specialize these 6 parameters, you find some surfaces which happen to be isomorphic to the algebraic varieties of the standard Painlevé equations. So ideally, what I'm trying to say, therefore, is that probably we shouldn't be describing the Painlevé differential equations by the surfaces that I gave you before, which were cubic in x variable. But if we want to reach some universality, we should instead try to describe everything in terms of Segre surfaces and of this form, okay? So let me tell you a few things, a little bit about this family of Segre surfaces. So first of all, they have a smooth projective completion. Then you have a divisor at infinity, and this divisor is actually a genus 1 curve, so you have an elliptic curve. And the nice thing is that it's universal. What it means is that if you write any other Segre surface generically, you will be able to find a change of coordinate or a smooth map that maps it into this form, okay? So this is universal. It's the most generic Segre surfaces you can write in this way. Okay, so now I want to confluence this. So this is called ZQ. I remember this is for an equation which is called QP6. Nobody stopped me there. It's a Q difference formulation of the 6 Painlevé equation. And Sakai tells us that we can confluence it to the standard Painlevé 6 differential equation. The way this is done is by taking a limit as q goes to 1, but not like in physics. Actually almost like in old physics. When q goes to 1, things become continuous, okay? It's really the idea of Q for the quantum, that it's a quantity which is finite and discrete. And then when you take the limit as Q goes to 1, your spectrum of your operator, instead of being discrete, becomes continuum. Everything goes to continuum limit, okay? So it's a continuum limit. Okay. And so we can take the continuum limit, and what we obtain is a surface which is very similar, but it has two main differences. One is that it lost one term in the second linear equation, okay? And two is that we lost some parameters. So we go from 6 to 4 parameters. And so if we look at the properties of these, with respect to what it was before, what we find is that the divisor at infinity is no longer an elliptic curve, but it's reducible, it's given by the intersection of two conics. So it's rather different geometrically. And so the first question we asked ourselves was, okay, so for the Painlevé differential equation number 6, we have our moduli space that we love, that everybody tells us is the right moduli space since the 80s. We are all convinced this is the right moduli space. And now we say that it should be this one. So we need to prove this, right? So I need to make a map between this guy, my Segre stuff, and this guy, okay? That's the first problem, and then I'll come to the next problem once I go there. So, okay. Right, so let me remind you, this guy has 27 lines. A Segre surface has 16 lines. So whatever is going on, it's not so smooth, okay? And, okay, so what we need to do is to reduce the number of lines before we try to build any map, because I don't map 27 to 16 normally with a function. I mean, with an invertible function, certainly not. Okay, anyway. So what we did was to do a blowdown. We blow down one of the lines at infinity, and what we found is another Segre surface. So now from this surface, we constructed a Segre surface, which we call Y Segre. This guy still, however, has 16 lines like the Z guy, but it's not the Z guy yet. We need to build the isomorphism, okay? So to build the isomorphism, there are two approaches. One is brute force. So what is the brute force? We have two Segre surfaces. Each of them has 16 lines. And the idea is that if these are isomorphic, lines go to lines. Intersections between lines go to intersections between lines. Therefore, you could feed into a large computer the most possible general free linear map, and then impose that this linear map maps lines to lines and the intersections to the intersection and work out. Well, first of all, I haven't found any computer that can do this for this problem. It's a little bit large, but it's also not as well defined as I'm trying to sound, because I'm saying I map 16 lines to 16 lines, but I'm not telling you which line goes to which line. And I'm telling you I map intersections to intersections, but I'm not telling you which intersection goes where. So actually this approach will never work. And so we had to come up with something a little bit more creative. And the something more creative is that when you have a Segre surface, on it you have special objects which are called Turing ratios. These are, in algebraic geometry, they are some special quantities that you may think of, well, okay, on the plane we have rational functions. They are our building blocks, okay? On the elliptic curve we have elliptic functions and theta functions. They are our building blocks. On a Segre surface you have a Turing ratio. That's your building block to build everything else. And what is nice is that in the confluence procedure from the QP6 to P6, the Turing ratios go to the Turing ratios. And what we could prove is that Turing ratios in the Q Painlevé 6 are related to the asymptotic behaviors of the solutions of the Q Painlevé 6. And equivalently, the Turing ratios are actually related to the so what we wanted to do was relate the Turing ratios of the differential Painlevé 6 to the asymptotic behaviors, okay? And we knew already that the asymptotic behaviors of the Painlevé 6 were related to the cubic, to the XX algebraic variety. So by a procedure of matching the asymptotic behaviors and the continuum limit, we were able to establish this isomorphism. And when I say establish, I mean establish. So we have actually a disgusting, if you like, but still explicit map that tells me that the z's in my Segre are some functions of the x's, and these functions depend on some objects which we call nu and epsilon, but they depend on the parameters of Painlevé 6. Okay?
This computation is explicit? I mean, you use Matemàtica or?
Yes, this computation is explicit.
And you use Matemàtica?
Yes, you use Matemàtica for this, for sure. But this computation is, well, I think with using Matemàtica, I use Matemàtica a lot for my research, but it is very much guided, okay? So it's not like, yes, I think we had a debate about this, right? You organized this beautiful seminar by Terry Tao and the round table around it. I think the point is that when you try to use a computer to solve, you have to guide it, and without guidance, you're not getting any results. So anyway, so we have this isomorphism, and then what we wanted to do was to see if we can give a Segre surface for every Painlevé differential equation. And this is, in fact, possible. And thanks to this very explicit formula, because we know how to confluence the algebraic varieties, if we can confluence the isomorphism as well. So we were able to create a list that for every Painlevé differential equation gives the associated Segre, okay? So you will have Segre surfaces for each one of them. Okay, so what is the moral of this story? Is that, what have we achieved? What we achieved was to unify the yellow part, highlighted in yellow, of Sakai diagram, okay? Then there is the green part. The green part in Sakai diagram, we think we can do it by almost for free by confluence, because confluencing is always easier than trying to go backward, okay? So the green part, it's a matter, I think, of time until it will be done. The problem is the left side, and so what we expect here will be some higher order. So I don't think the Segre surfaces that I've given you will also be valid for the pink part of the diagram. We expect to have some higher order surfaces, okay? Some higher order del Pezzos, maybe. And going elliptic, who knows? Actually, some conjecture we did with Rubtsov and Chekhov is that for the elliptic case, we should have some del Pezzo, but in weighted projective space. So hopefully one day there will be this, and then we will be able to confluence everything, but so far only the yellow part is done. So anyway, thank you.
That's all?
That's all.
She wants more.
I was excited. Thank you very much for the talk. And now we proceed with the questions. Preguntes? Do we have questions here?
Yeah, thank you for the talk. So when you blow down the Del Pezzo surface to get the Segre surface, are you not, did I understand that this is what you do, right? You don't eliminate information by blowing down? Like, it seems to me like somehow the
Yes,
Del Pezzo is more general. So how do you recover the Del Pezzo from the Segre? Can you like do that? Or
You can blow it up.
and this
Yes, yes.
there's like a
Blow up and blow
unique
down.
procedure.
Yes, yes,
Okay.
yes, yes.
Sorry,
yes,
then that's
yes.
a stupid question, sorry.
No, it's okay, right.
Okay, well, that was my question.
Good to make a stupid question. So more questions.
It
We will
wasn't a
not judge
stupid
the questions.
If you've never seen blow up and blow down in algebraic geometry, how can you know that they are invertible? It's not a stupid question.
No, that's a good question. So more questions here from Xavier has a question.
Thank you very much for the talk. So it's an amateur question. So this first list of equations of Painlevé, so it's like you are somebody, Painlevé perhaps, was trying to get a list of equations for which you have special solutions of a certain type, and then there are, I don't know, it was 6 of them, but meaning I can understand that you can imagine equations that give you these special solutions that you are looking for, but a priori it looks like the list of possible or eventual equations for which you have such solutions could be like infinitely many of those. So I don't understand why these 6 equations are so close. I mean, like
Okay.
this is the list of
Yes,
6.
because he was, yeah, that's a very good question, in fact. And part of my work many years ago was precisely to answer it. So let me go back a little bit. You see, he's sticking to second order, right? Painlevé was sticking to second order. So he's saying, I consider second order differential equations. But why? Okay, so first order, if you impose the Painlevé property, you don't find anything new. So it went to second order. Of course, I could try third order, fourth order, fifth order, okay? And that's in fact what a lot of people are trying to do now. So the list I've shown to you, the Painlevé list is limited to second order. The Sakai list is also limited in some sense to second order Q difference and difference equations. There are higher order Painlevé type equations, for example, the Garnier systems, the Schlesinger systems, there are many, many, many. There is a little bit of a problem, if you like, in defining now what we mean by the second property. So, so what do I do at this level, right? So suppose I have a fourth order Painlevé style equation. When I say that the solutions of this fourth order Painlevé style equation are non-classical or new, do I allow the solutions of the second order Painlevé equations or not? Okay? So do I allow to go and add some operations in this procedure in which I say solving second order Painlevé equations is allowed or not? And this is opening a can of worms. So for some years, we did some work also with Dubrovin, and then there was work by logicians, Anand Pillai, who were approaching this from model theory. I actually came to Barcelona 20 years ago to discuss with people who were working in differential Galois theory, like Morales, to discuss this. The result is that it was way too hard, honestly. We just could prove something, but it was so hard that I think nobody actually went down that road anymore. Even Anand Pillai, which was approaching this from model theory, said to me, no, I'm not going to do this. I don't even know where to start.
Thank you. More questions here. Sebastian.
Thank you very much. Could you tell us a little bit more about your last line on the higher order?
Excuse me? The last line.
Yes.
This one? Which?
No, the last line of your talk, you mentioned the higher order. You expect a higher order.
See, okay. No, sorry.
Just to know a little bit, what do you mean by that?
Higher order del pezzo.
Yes.
Yes, not degree 3. Because yes. So in this table, I have intersections. Essentially, these are intersections of two quadrics, and they are isomorphic to something which is of this type. So this is the del pezzo of degree 3, because I have one triple term and then I have square terms, okay? What I expect will be, for example, x1, x2, x3 minus x1 to the 6, for example, okay? So higher order in the sense of the polynomial. Still in the cubic. Well, I don't know if it will be a cubic, but it will be equation with a higher order of polynomials.
I see.
Okay, so higher order means we blow up less points on the, yeah. Mm-hmm. Yeah.
Okay, thank you.
Some more questions? Just like, I'm very intrigued about this confluence and looking at the lines, but these lines are in a moduli space, right?
No, are parts of the moduli.
They are part of the moduli
Yes.
space. So do you have a way to understand this confluence on the lines? I mean, other than just...
Oh, you can follow the line in the confluence.
Okay.
They merge.
They merge.
They
And
merge.
this merging thing, like, because this reminds me of other blowdown that you see in other parts of geometry. Like you can blow up and blow down all the time, and you can merge and see how. I mean, do you have an interpretation in terms of invariants that are lost, or do you have a control?
Oh, that's interesting. No, I don't at the moment, but I must think about this.
Let's think about this.
Yes.
Okay. Okay, so let's thank Professor Mazzocco again.
Thank you very much.
Thank you very much.